The first concept we studied in electricity was current, the flow rate, cups per second, or amps. But you also know things are rated in voltage, 120 volts on the wall, 1.5 on small batteries, 9, 12 volts on a car battery. So we need to look at another thing that these things have, which is called electric potential difference or voltage. So you need to be able to relate voltage to the fall of matter due to gravity, define gravitational and electric fields for me, distinguish between the flow rate of a substance and the energy the substance is carrying in both electrical and mechanical systems, and explain how a battery is just a stack of cells that increases voltage, but not current. So let's look at what we call a force field. Here's a classic description of a gravitational force field. That as an object moves in, it falls into the well of gravity, just like things can fall into an atom as well. There are 4 fundamental forces that create fields in our universe: gravitational, electromagnetic, weak nuclear, and strong nuclear. We've studied weak and strong nuclear when we studied chemistry, and we're doing electromagnetic now. So think about gravity. There isn't any spot you can find in the room where it stops working. You can't hide from it. It penetrates all space. So force fields, in a way like a wheat field, describes a force that exists everywhere you are walking. Things move or flow when this force changes over space, like the well above. If the force was uniform across space, it would be flat and it would just sit still. So let's look at gravitational potential difference, which is something you study in grade 11. If we go to the Lord of the Flies, where they push the rock off the cliff onto the kid, in this case it's a nice ending, so he's going to successfully catch the rock. Depending on your height above ground, the rock will have different energy. At height 1, if you push the rock off, it's going to be caught and it's going to be okay. But if you take the rock to a higher height and push it off, it's really going to clobber the guy. So the rock at position 2 has twice the energy as position 1. Why do they call it potential energy? Because it's stored there. Potentially the rock could fall and hit the guy. The energy is not released till you shove it off. A campfire is not potential energy. It's being shed while you watch. So an example of a potential energy source would be a bullet sitting in the gun or a bolt from a crossbow sitting in its rest spot. It's ready to go. Okay? Now, the airbag launch. Only 2 things affect this launch height: the mass of the jumper and the victim, and how far the first person fell before hitting the bag. So we put energy in here and the energy came out here. The speed or the energy of impact of the person on one end of the bag determines the height the other person will reach. We trade off one form of energy for another. So let's look at current flow. Instead of a single rock, we're going to turn this into a waterfall now. Both of these streams are flowing at, say, 100 liters per second. So they have an identical current, but the stream falling from H1 height has less energy than the stream falling from H2. So you can't say these 2 flows are identical, therefore it will feel the same standing under these 2 waterfalls. No. This one has much more energy than the other one. The energy of the fall is a separate concept from the volume of flow going over. Now here's the problem that I get with students answering a question, the causation. Does the current create the fall in altitude, or is it the change in altitude that causes the water itself to flow? So what has to come first? The fall itself or the water going over the fall? If you think about it, if there was no change in height, the water would have no reason to fall. Therefore, until you have a change in height, the water will sit still. Turn the flowing water to flowing electrons. Unless the electrons are put through the equivalent of a change in height, which we call voltage, they're not going to move. Voltage or electric potential difference must be created before any current flows. This is totally explained in the conductor and insulator slideshow as well. So you can follow this link below and see more detail on that. So in conductors and insulators, we talked about this, that in an insulator, the electrons are stuck down, and in a conductor, they're not stuck down. So the voltage is this lift. So this is the conductor and insulator slideshow. We have this lifting action, which is our voltage. Now, what does it mean to lift electrons so they flow? That's a lot more complicated, but this is a model or a metaphor that the voltage is like creating a ramp. The steeper the ramp, the faster the flow. Now, not everything flows that easily. Some things like this, like the metalloids they call it, the semiconductors, they will allow electrons to flow with a good ramp, and then they will begin to flow. Okay? Now let's look at the voltage of a power source like a battery. Think of each set of plates in a battery. So a cell is a stack of 2 plates. So this guy down below here that I can't bring the arrow too close to, where a battery is a stack of cells. So in a traditional 1.5 volt battery, there are two metal plates, and that lifts our diver up. So that's why I got the little 1.5 volt battery next to it. A 9 volt battery simply increases by adding stacks of plates on top of each other. So if you split open a dead 9 volt battery, can't be alive anymore, you'll get an explosion. One of these batteries that's long dead, if you cut it open, I did as a kid, you find a stack of plates. Each stack is 1.5 volts till you get to 9. So the total number of electrons may be the same, it's just the height they're diving from. Now, what about on your way down? Well, think of it like this. If voltage lifts the electrons to a higher energy, then as they lose energy, it is the equivalent of falling. We can be lifted up to a specific height, but drop back down to the ground in stages. So right till now, we've been looking at the idea of just jumping all the way to ground. But a circuit doesn't necessarily do that. A diver jumps all the way to the ground, but a skier may not. So this skier enters a 9-meter ski lift. Doesn't matter how shallow or steep it is, he gets lifted 9 meters in height, and he could ski downhill like this. Alternately, a skier could be lifted up, or electrons lifted up 9 volts in height, and they could drop 2 volts on one part of the circuit, 7 on the other. But whatever height you were lifted to is the drop you must experience later. And that would explain this guy. He gets lifted 10 meters in the air, he falls 10 meters. If the bag were turned around and he were launched at the cliff instead, he might go boink, 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 out, 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 and drop all the way to the ground in several bounces. So sometimes it's one lift up, one drop down. Other times it's in stages. So here's a one drop situation. This would be a continuous drop, a single drop, and then we have a drop in stages. But it's really easy to see what goes up must come down. And next we're going to look at lifting in stages.